Hi to everyone here. Glad to have the chance to share this work with you today. So I'm going to talk about activity understanding. So we're really talking about video understanding, but let's also note that massive portion of video is about people, what they're doing. And so it's almost interchangeable. Activity, human activity, video understanding. We care so much about this for a lot of very central applications, big domains like robot learning. As you may have seen, there's a lot of excitement about being able to have robots that learn, not just from their own physical experience or teleop or simulation, but actually from us, right? By watching video and seeing how we do complex activities, especially dexterous ones. And another big area that really motivates this kind of work is thinking about the AI assistants of the future that can be more and more embodied, for example, on smart glasses, where we could have just the information we need based on our physical surroundings, what we're doing, and succeed more at all kinds of tasks. So this motivates why we should care at all about video understanding, and I hope you can see these are two big areas where it is fundamental. But let's talk for a minute about the challenges, and I mean the state-of-the-art challenges, so the ones that are really affecting the best models we have today. So number one, fine-grained detail, especially talking about temporal detail. So take a look at these two videos. See if you're noticing anything special about them. As you watch them, you might start to notice one is kind of the other one in reverse. And in fact, it is the same video played forwards and backwards. But this kind of detail, that temporal directionality, is really missing from today's models. And I'm going to show you how and why in just a minute. So that's one challenge. Another key challenge is viewpoint versatility. So if you think about seeing an action from your own perspective, we call this the egocentric perspective, versus seeing it from as a spectator, as you watch someone else do something, so that's the left and right views respectively, of course what you see is so different, and how much is visible, what parts are emphasized, how much you know about the actor versus the scene, this is all changing, and these dramatic viewpoint changes are hard for activity models. Third challenge, 3D. So in particular, thinking about activities not as very small temporal glimpses in time, which we in the field have for a while, but instead thinking of long video, of activities that unfold in a 3D physical persistent environment where some things stay put, other things don't, but just the movement through the 3D space itself is significant. And then the final challenge I want to highlight at the top is compute and expense. So maybe a less glamorous problem, but the fact is we spend so much of the compute and video understanding on extracting the initial representation, so 99.9% without exaggeration. And so we are looking to more effective, scalable ways to even get the best representations we can. All right, so then thinking of those challenges I just motivated, this talk is going to look at 3 examples from our recent work, how we're starting to deal with them. And I'm going to start with that time sensitivity. And here I'll introduce to you some new work we have called the arrow of time in large multimodal models. Then I'll talk about another multimodal effort, starting with some data foundations. This is a large collaborative project called EgoXO4D. And that'll help support some of those challenges I just motivated, including thinking of 3D spaces as the home for human activity. And then the final bit of the talk, I'll touch on some of our work for making activity, human activity, multimodal, and in particular 4D, so really grounded in 3D spaces. So that's where we're headed for the rest. Let me talk first about the arrow of time. So this phrase itself comes to us from science, and it's capturing this fact that we perceive time with a very strong direction. And so, the relentless forward march of time. And this is different than how we perceive space. Right? And so this is remarkable, and it's something we do naturally. Here, I'll show you. Look on the right side of the screen. Here's a few videos where kind of the temporal directionality of the actions that are happening here is very strong. Right? The building fell down, the people are marching forward, the billiard balls are dispersed on the table. And so this is true about our reality. We see things one way, and we're very sensitive to what that direction is. But I can tell you that's not the case for today's best large multimodal models. And in my slides, I'm going to use LMM for large multimodal model, so visual and language, not to be confused with LLM for a large language model. So these best models struggle today with this arrow of time perception. If you were to give these two videos, which again is on the left played forward. Did I get it right? On the left played backwards, on the right played forwards. The best models today cannot tell the difference. So they won't distinguish which one was which. And similarly, if I were to play this video and ask for a description from today's best models, actually it'd be pretty good, and it would talk about the burner igniting. But if we play the video backwards and ask the same question, we actually get a similar answer. And why would that be? Well, there's just such strong semantics built into the language priors that have trained these models so well that you can expect that some of the more common activities are attached to roughly similar visuals, even when the details don't support that. Okay, so those are anecdotal examples, but this is just true at large. So here we tested across 9 different benchmarks that are very popular in the community, and we looked at what happens if we feed in videos the right way, like the wrong way, meaning in reverse, or just like in a shuffled temporal order. And what you're seeing by all these little rectangles showing you the clusters of accuracy across each of these 9 benchmarks is that those are kind of flat. And this is disappointing, right? It means that no matter if you had the right video or the temporally wrong video, you get similar answers. You get similar accuracy. And so there's little or no performance degradation despite these frame order changes. Now, what do you attribute it to? This is actually complex as well. So it can be both the models that aren't time sensitive. It can also be the benchmarks that aren't demanding time sensitivity from the models. And we dig into this a little bit. It is indeed both those things. And so we're doing some work to try and counter both aspects, both the benchmarking, the data, what are these question answering data sets with video really requiring, as well as the models that can be more time sensitive. So on that first part for benchmarking, we developed an automated score that we could apply to Q&As on videos to score or quantify exactly how time sensitive are they, and it has to do with just seeing what are models' predictions, sensitivity to the video's temporal direction. And so we could rate data sets, and here the ones that were low on temporal sensitivity on the left, the ones that were high on the right. And the good news is that the ones on the right, these are recent efforts that folks are trying to put more temporal specificity into the tasks. And so we'll come back to those a bit later when I show you some results. But now let's talk about the modeling part, what we could do here. And so here's a sentence about the main idea. So we said, okay, video models, they're not telling the difference whether videos are forward or backwards, or just think in general, they're not sensitive to the fine-grained directionality of activity. And so our idea is to treat this in post-training with reinforcement learning and introduce a reward that says what kind of answers we like from some initial model. And this is in particular, we're going to reward models that have divergent responses between a forward-played video and a backwards-played video. So let me show you what that would look like in an example. Suppose this was a training video, and on the top left, this was it. This is a forward clip, and this is a person doing something, going into the closet, getting something out. And the question attached to it is, why does the person step into the closet? So here comes this reverse reward I just described. Let's look at an example. First, we have the ground truth answer for this question in training, and here it is. Person steps in, gets something, retrieves a brown box. Now, the first thing we do in training is reverse that video, and that's that second clip on just to the right of it. And you'll notice that he's just doing the same thing, but now in reverse. And I just mean literally playing the frames backwards. And now we'll say, okay, what's the reverse response according to the current model we're training, and with the same question. And so with the reverse video, the response looks like this. He's placing the box inside. He must be organizing or storing it. All right, so then finally, what happens in this reinforcement learning post-training, we want to generate multiple possible responses from the model for the forward video, the proper video, and the question. And that's what I'm stacking on the right of the slide. Here are 2 such sampled outputs. Candidate response 1 talks about looking around in the closet, retrieving a box. Candidate response 2 talks about placing the box in the closet. And these 2 I showed to highlight here because they illustrate how, okay, we're going to prefer the ones from our model on the forward video that produce a dissimilar response as we got on the backwards video. So that would be rewarded. That's a good one. Whereas the ones that are saying something similar to the reverse video, this would be discouraged. Okay, so that example sums up the approach, and putting it together with the full kind of machinery. This is this model that we call ArrowRL for the reinforcement learning component. We're relying on an existing framework called Group Relative Policy Optimization, or GRPO, to do this post-training. And so you have your training videos like we saw. We reverse it one by one. Then we look at what the reverse response is. That's the twiddle at the bottom there. And then we'll do that sampling of responses like we saw, say big G of them. And now we want to know, okay, how good are they? And there's actually two parts to this reward. We don't just want any response that's different than the other. We want it to respect the ground truth as well. So that's the first part of the reward that says, how similar is this candidate response, OI, to the correct one, O star? And then we'll call that the fidelity reward, fidelity to the ground truth. And then this reverse reward I already described. And this is the one where we say we like the ones more when it would be different than the response it would give for the reverse video. And so this is how, during training, then we're rewarding the kind of samples we like and improving the original policy, or this large multimodal model. All right, so let's see what it does, and in fact, how we can benchmark it. Part of this work was to, as I've alluded to, establish a benchmark that really is time sensitive and kind of increase the requirement there. So first of 3 tasks we put was sequence direction classification. You get the 2 videos, you need to say which one is played in reverse. Second task would be directional caption matching. So similar idea, but here you're saying, okay, this is a language description, like someone taking personal care items out of a clear plastic bag. Which video does it go with? You can do this in either direction, video to text or text to video. And lastly, we have, if you think back a few moments ago when I showed you some of those more powerful time-sensitive benchmarks, we kind of pooled across them, found the most time-sensitive, challenging problems, and put together a VQA data set based on those. All right, and so the main thing that happened then, if we evaluate across this arrow time benchmark, AOT bench, those are the cluster of left columns, and we do the same on those temporal sensitive benchmarks on the right, we're looking at a series of different base models from the LAVA, Quen 2, Quen 2.5. These are all well-used, effective, open source models for large multimodal question answering here. And we've, in green, are showing, okay, what's the gain we can get if we put in this AOT sensitivity? And the encouraging thing is there's pretty consistent gains. Some of them are even quite large. I guess the gains here are somewhere from around a point to even up to 21 points in accuracy difference. And here's some examples of what it looks like. So our favorite burner from a few minutes ago, if we were to say with the base model what's happening, it thinks it's being ignited, but you all know now it's actually being turned off. And the refined model with our time sensitivity is getting it right. This one that's describing in the base model, that's the top caption about the scene in a pretty realistic way, but it gets more time sensitive in the bottom response. You can see it's talking, in our case at the bottom, about things like the clouds transitioning from lighter to darker shades as the light diminishes. And that's very directional. Final examples I'll show for this. Here's one. Pay attention to what order the person does things in this video. So did they distribute first, or did they shuffle first the cards? Again, if we ask the base model, well-trained, the answer would be that they were shuffled and distributed, but in fact, it's the reverse. And my last one here, this is a great one both for time sensitivity and spatial sensitivity. The question is, what's the order of the letters on the table at the end of the video? Right now, they're in a very nice language-friendly order that says storm, but as time goes on and they get shuffled, you'd need to understand that time sensitivity, and base model can't yet, but we're making that improvement. Great, so I just showed you how we're starting to deal more carefully with this really widespread failure mode for today's LMMs, and that is to start injecting this arrow of time. And I want to now shift into thinking about aspects that are, again, multimodal. Here we're going to be talking about an even broader set of modalities, and also thinking of that challenge I motivated before of saying, how we view an activity really affects what we can perceive about it. So this is an effort, we released open source data set last year called EgoXO4D, and I'm showing you samples from this public data set. Again, it was this collaborative with all the folks and institutions you see at the bottom of my slide. So multi-view, so there's egocentric capture, that's a wearable camera on the left-hand side of this grid, and then exocentric camera, this is third-person cameras in the same environment, time-synced to that wearable camera, showing you the same activity, but now from 4 or 5 different views, and that's on the right-hand side. And so EgoXO is special for this, having very high-quality time-sync multi-view data. It's also got a focus on fine-grained human skilled activities, so skilled human activities. And so you're seeing some of those domains go by, things like cooking, sports, there was bouldering, dancing, music, first aid, bike repairs. These are all things that, think about my robot motivation, right? We'd love to start to translate some of these complex dexterous activities to robots. Think about the AI assistant kind of motivation, where we'd love to have skill assistants helping us learn new skills based on our own current performance. So all the activity is skilled human activity captured from these different views, and you can see kind of the complementarity and what might be interesting across them. And all the people who took part in the data, meaning the ones actually in the videos, these are people with varying skill levels by design. So zooming in a little bit on a single example, in EgoXO4D, the EXO cameras, here are 4 of them facing the same subject. This is a professional chef cooking in a meta kitchen and wearing the glasses. And so what you see then is those EXO views, but you also have what they saw from their own first-person perspective, which is the video here on the left. Furthermore, those glasses are heavily instrumented with multimodal sensing. So you have 2 SLAM cameras giving us good 3D reconstruction. We'll see in a minute. You have eye cameras giving you the eye gaze of the person over time, which is so fascinating when we're looking at understanding skilled human activity. And all the other sensors you see here, also including multi-channel audio. So what I think is quite exciting about this data, again, capturing skilled human activity, but also letting us to ground high quality, but very real world human action in these skilled actions in the 3D physical environment. And that's what you're looking at here. These are 3D reconstructions provided with the data set for any of the environments. Those are reconstructed camera poses in white, and then the green one is the ego camera. That's the person's head-mounted camera. And that red bar is their eye gaze over time. And so this is just a resource ready for all kinds of work. I'll show you an example from ours just a bit later in this talk. But again, what's really exciting, I think, is being able to bring this dynamic activity into the physical 3D environment. Now, this collaboration, EgoXO4D, a precursor effort we did called Ego4D, part of the effort was, and maybe the first part was like, let's amass the right kind of interesting data that can push our field forward. And then the other part was like, let's put forth the benchmark tasks we think will help push the modeling as well. And so this is an array of the kind of tasks that this team has put together and have been hosting challenges for some years now. And I wanted to highlight for you what a few of them look like. Starting with the EgoXO4D, here I motivate at the beginning kind of this challenge of thinking of different viewpoints for activity understanding, as well as the 3D persistent spaces. And here's a task where the models need to look at the video, even just from the ego view on the left, and be able to decide what kind of key steps are happening over time. And so that color coding is saying, okay, over time, these are all different chunks where different relevant human actions are happening, and we need to be able to describe them in words. So that's the key step recognition task. Here's one that deals with that cross-viewpoint challenge. Look how different the bike looks on the left from the ego view versus on the right from the exo view. It's a great example of how the aspect from which you view something will change what you see, and yet we need to be able to associate. And so this challenge, ego-exo relation, is about being able to say, okay, if I give you a mask on the ego view, can you anticipate where it will be in the exo view? And even, of course, without strong camera localization given to you. So that's a relation task. Proficiency estimation, this is where it gets real interesting about the fact that these were skilled people doing skilled activities. here's a video on the top from a novice climbing the wall. There's a video on the bottom for an expert. Again, ego, exo. And so we put forth a challenge called proficiency estimation, where the job of the model is to say, is it a novice or an expert? In fact, we break it down across 4 different levels of expertise. And so think about the subtlety then we're starting to demand from these models to get out what is the actual skill level based on the way they perform the activity. And then finally, the other task I wanted to highlight for you is body pose. So, of course, a classic computer vision problem, lots of work over decades, pushing the envelope. Some researchers want to think about understanding human body pose even when we don't see a lot of the body. So think about that wearable camera, and then think about how much of the body do you see. You actually, depending exactly on the camera itself and its positioning, you may see very little. You may just see the hands occasionally. But there's a lot of structure in how we move our bodies and what we see as a result. And so even the ego-only body pose task is quite interesting. And we have annotations, all kinds of data to support that, both for the body and for the hands. Great, so I kind of gave you a little bit of a glimpse at some of the tasks, again and again in this kind of formal benchmark that our team put together for the broader research community. And it's healthy and growing, as in, at this point, more than 100+ teams have competed on these challenges from all around the world. We've hosted the challenge at least 4 years now and counting, and it's fun, and we get to find out, in a very rigorous way, how is the field progressing on these ego understanding challenges. And that's what the right-hand chart shows you. It's showing the percentage improvement over baseline over time as we run these challenges, as these different teams are competing to make better systems. Great, so I've shown you time sensitivity as a failure mode for today's large multimodal models, what we can do about it with this idea of injecting the arrow of time. Now I showed you a resource that's supporting our work and many others for activity understanding with many modalities, with multi-view or cross-view data. And then the final bit of this talk, I'm going to cover 4D activity modeling. And here I'll refer back to ego exo in one example, and we're going to see how we're thinking about making activity less of a 2D short time frame kind of problem and more of a long form video and 4D or 3D kind of problem. So let me explain a bit more. I said at the beginning that video features are expensive. Just doing the extraction of video representations can dominate a model trying to do some understanding. And the norm really is to just think densely across time, kind of pulling features and getting these features sequentially. But we had this idea that would draw on multimodal sensing that could be less expensive. In particular, here we're going to focus on IMU, so we can have IMU sensors with our cameras that are relatively low power compared to running an RGB camera. And the idea was, can we approximate what we see in these full RGB computed video features with much less sensing? And all the way to the extreme of one frame. So think of a short piece of video. What if we took just one frame from it, but also knew about how the head was moving, which of course is how the camera is moving. And that's the little camera pose you see at the bottom in 3D. So the thought is that, okay, they carry different things. So from one RGB, you actually do get a lot of semantics. So time changes slowly, and so the semantics don't change abruptly as you start watching a video. By semantics, I mean what objects are there, what's the scene like, what are they doing? And then the camera motion tells you something about how it will change within that physical 3D environment. So for a thought experiment for you, just to stay with me, think about if you saw that frame on the top, and then you knew the camera was going to move as in the bottom in the next couple moments, can you kind of picture what the video would look like? Certainly not fully, but you would be able to anticipate some aspects of that content. And so we decided we can look into trying to approximate what we do know about a short video clip using just those simpler and low power, less compute kind of requiring sensing. So in particular, we set this up as a distillation problem. You say you've got a video clip, you've got a frame or K-frame, some small number of frames, and you have this camera motion from IMU. Then can we distill from the heavier model. So we'd like to have the full feature, whatever our favorite feature is on the full video clip, but instead we'll approximate that feature. We'll learn how to train just from those simpler inputs, the frame and the RMU, to approximate that expensive feature. Okay, so you've, during training, extracted all the heavy features from all the training videos, and now you learn how to approximate them using just that simpler input. And just doing that means you'll use 200 times less GFOPs. And furthermore, even if we hold, that's compared to the original more expensive representation, even if we hold this idea up to what were the best kind of efficient video recognition methods that try to do other things using less frames and be smart about the computation, here are these charts on 2 different data sets, which happen to both be egocentric. Then the accuracy is on the left, on the vertical side, and the compute is on the bottom. So you'd like to be very accurate and not so expensive. That would be the top left of both these charts. And what I'm showing here is kind of what you can carve out depending on exactly how many frames you use, the trade-offs for these different models. And ours is shown here in purple. Some of the others are doing things like drawing on audio as a lighter signal, being smart about which frames, and so on. So this was one way to think about really bringing that 4D structure into the representation itself, because you're talking about what we see in the environment combined with how we know we're going to move in it as being a good way to quickly encode what we see. The last example I'm going to give you continues on this thread of 4D activity understanding. And now, if a moment ago I was motivating in terms of cost and compute, here I'm going to motivate in terms of 3D structure. So the other thing not to like about this kind of status quo approach of just seeing video frames go by and densely, uniformly extracting representations is that it is very 2D, meaning it thinks of the world as kind of whatever comes by the front of this camera, as opposed to something that really exists surrounding the camera, right? And that's only accentuated when you talk about wearable, egocentric cameras. So just to help see that picture, on the right-hand side, this is the real world. Well, it's not. It's a sketch by one of my artistic students, but this is the real world surrounding that tiny little aperture you're seeing over time. What we ought to be doing is grounding everything we see in that unfolding video in that same 3D space. And that's what I mean about a persistent 3D spatial context. So taking that kind of motivation of what's wrong, what we ought to rather see in our video models, let me show you this example we call fiction. This is an acronym we made for 4D future interaction prediction. And back to what I was saying a bit ago about EgoExo and kind of grounding human activity in the physical space, this is what we're going to do here. And in particular, we want to be able to observe some past video, some video up to time t, in a 3D environment, and then anticipate 2 things. Where will be the next interactions in the scene, and how? And specifically, we mean where in the scene will the person be when they interact with some other object? A lot of human action in physical spaces is driven by using things in the environment. Kitchens are a prime example, but not exclusive to kitchens. And then how? So by how, we mean how will the body be posed as we look forward in time? So if you just think about the tasks as anticipation or forecasting, saying if you observe some of the video, what's going to happen next in this kind of 3D grounded way. So I'll show you how we started to process then video, like here it's EgoExo 4D, to start discovering what are 4D interactions. So what you're seeing here are a bunch of objects being detected across video frames. And then when doing this across the different frames, we can back project to the 3D point cloud and have full 3D objects detected. So 3D object bounding boxes like you see here. And these are things like stove, canister, sink, anything that's detected in these scenes. So that'll define for us the wheres, so where objects are in the environment that might be interacted with. And then for the how, we're extracting the body pose. Here we're using a state-of-the-art method called WAM to get these precise 3D body poses and shapes over time and putting them in the same coordinates as that 3D environment and where those objects live. Okay, so this is amassing kind of with best methods from vision, where the activities are taking place and how the body's moving to do them. And then finally, we'll decide that the moments where interactions happen are where that person is using their hands to interact, meaning intersect some one of these 3D object volumes. So if you think about what's happening here, you have reams and reams of video. It's unlabeled, but because of the structure in it and the spatial structure across the views, we can prepare it to find out all these 4D interaction points. And with that, we can train a model to do that forecasting task. And the model we train is an autoregressive model. It starts by encoding the different inputs, the video, the environment where those objects are, and the body pose as multimodal tokens. And then for output, we're learning to decode into those two variables I talked about. On the top, where. So where is the person interacting in the environment? And on the bottom, the how. And this is going to return to us at every voxel in the environment a distribution from which to sample the body pose. Of course, the future body pose. So again, we're observing some video, and then we're going to anticipate what the person will do next. Let me show you an example. So here, you get the video on the bottom right. It's in a place you, the model, hasn't seen before, with a person you haven't seen before, and we'll start doing this processing where we observe the body pose. Here it's in dark pink when we've actually observed it. All this we observed. This is at inference time. Okay, so they're doing something in this kitchen. We can start to, the model can start to anticipate, okay, based on what they're using, okay, the light pink ones and those positions are where we expect we'll see activity next. And as it turns blue, this is where the future is happening, right? We didn't see the blue ones, but what we like to see in this result is that the blue starts lining up with all those light pink ones that we had anticipated. And so here's one, again, another. So as time marches forward, then we start to see whether or not our predictions came true. And what's neat about this is, again, you're being able to come into a new environment, new person, and having learned this kind of structure of activity with respect to places and objects, you can expect what they might do. Okay, well, they're acting over here using this. They may need to use that later, and to get to that, they have to use their body, reach down or reach up, and so on. And so that's what you saw happening in this example. Let me show you another one. This one is in a person in a bike repair shop. And again, same format. So we observe the video on the bottom right. We start extracting the person in the scene and the big video here. And the dark pink poses we've observed. And then at a certain point, video goes away. And I'll tell you when we reach that point. Right here, and now we're anticipating those light pink poses, where they're going to be, what and how they'll be using their body to do the action. And then the blue is what the future video actually held and what we're seeing there. And again, the more they align with what we're anticipating, the more successful that prediction was. And you'll notice that these are not indexed by time, as in, there's time, and then there's, okay, what's going to happen next in the some 30 more seconds. And this is considered a pretty long form kind of anticipation problem. But you can also imagine on top of that an extension to index those predictions in time. Our thinking in doing this in the kind of temporally pooled way was motivated by thinking of how the space is going to be used given what we've seen so far. And for that, not necessarily in a time order, but to know kind of the affordance of the space given what the person was doing already. Okay, and of course we quantified how well is any of this doing compared to best models. In fact, taking best models, we generally had to upgrade them to make them have 3D outputs, because as I've mentioned, a lot of this work is really still taking place in 2D. Okay, so we're coming to the end here. What I've shared with you today is all about activity understanding in video, especially leveraging our multimodal sensing, whether it was IMU, language, and kind of this platform of data for EgoXO4D. I shared a few different model ideas with the AeroRL for instilling temporal structure, 4D activity data in models like fiction we just saw and EgoXO, and this idea about making cheaper video features through multimodality. And this work is done with all the folks you see here at the bottom, including the student first authors, Sherry, Ashutosh, Shuhan, Romy, and my colleague George, and of course the EgoXO4D consortium. And with this, I'm going to stop and be really glad to have any comments or questions from you. Thanks.